Thank you so much, and thanks for the welcome and the introduction. It's really an honor to be here tonight. I'm pretty excited that my talk got scheduled in the break between the snowstorms so that I could actually make it here. We've had a pretty exciting winter down in southwest Colorado. We're getting buried in snow, which is made for some really fun skiing, and it's going to be an exciting water year. So what I'm going to talk about tonight is the importance of snow and its relationship to our water supply in Colorado. And so I'll do a little brief intro there, and then I'll give you a sort of a primer on properties of snow, and then I'll talk a little bit about the monitoring that we've been doing and some of my adventures that I've had in monitoring. I'm actually new to the field of snow hydrology. I've been a hydrologist now for 30 years, but have focused mostly on rivers and our impacts on rivers as we build dams and build levees or remove tamarisk. But about 3 or 4 years ago, I got started with a project with a professor at Colorado State University, and they were interested in looking at snow on the Grand Mesa. So that was sort of my intro into snow. And then I'll give you a very brief update on where we are right now in our snow year. But before I start on any of that, I just want to lay out a few basics in the field of water, especially in Colorado, and how we talk about water. And one of the things that we have a different calendar year in the water world, and when we talk about water, we talk about the water year. And our water year starts in October, and it ends on September 30th. So our 2019 water year actually began last October. So the water year is named for the year that it ends in, and you can think of it being the year when the big snow melt peak happens. So our water year encompasses all of the snow that we accumulate through the course of the winter. So several times through the talk, I'll be talking about the water year, so you understand it starts in October. The other piece, whenever we talk about climate and hydrology, we often are comparing what's happening to what we call as normal. And so one of the big questions is, of course, what is normal? And in the climate world, in the weather world, we often compare what's happening now to what happened over the average of a 30-year period. Are you going to switch mics? Okay. Is this better? Okay. All right. So we often compare what's happening now to what happened over the average of a 30-year period. And usually, what we'll do is, so for example, before 2010, we averaged from 1971 to 2000. After 2010, we now compare what's happening now to what happened between 1981 and 2010. And the interesting thing about that transition is that, so we left off the 70s now, is that the early 2000s is actually a warmer and drier period with lower stream flows. And so what we're doing now is comparing what's happening now to a drier period. So if we start noticing that things are drier now than normal, we're comparing to a drier normal even. So it might even be more dry now than it would be if we were comparing to a different time period. So it's always good to look at data and question what is normal, what is the time period we're comparing to. The last little sort of bit of intro I'd like to talk about is what is an acre foot of water? So when we talk about large volumes of water, we often use this volume of an acre foot. And an acre foot is an acre of land with a foot of water on it. So you can think of it as a football field with the end zones, 1 foot deep in water. And that's about enough water to supply, depending on how much you water outside, 1 to 4 households with water per year. So to put that in perspective, Blue Mesa Reservoir, which is our largest storage bucket in the state of Colorado, is about 1 million acre feet. So that when we talk about we need to supply 7.5 million acre feet to the lower basin because of the Colorado River Compact, we have to supply 7.5 Blue Mesa reservoirs to the lower basin to meet our Colorado River Compact requirements. Okay, so let's talk about snow now. So we all know snow is important in Colorado. It's important globally. it is a significant contributor to runoff and water supplies for a lot of the northern hemisphere. And in the Colorado River Basin, up to 80% of the water per year can come from snowmelt. And in the United States, you can see where most of our snowfall is in the high mountains, in the Rocky Mountains, and in the Sierra Nevadas and the Cascades. About a sixth of the world's population gets more than half of its runoff from snow. And in the western US, 80 to 90% of our renewable water, and renewable water means our surface water, not our groundwater, is coming from snow. And one of the interesting things about snowpack and snow melt is it is a more efficient transformation of water into our rivers than if it rains. So when it rains, we lose more water to evaporation and transpiration than when it snows. So water is actually, snow is a more efficient way to get water into our rivers. And so because of that, snowfall is contributing proportionally more to our runoff and to our groundwater than rainfall does. And here in Colorado, of course, we know we have a large range of elevations, which produces a large range of precipitation and a large range of snowpack. And we can think of our mountain snowpack in Colorado as our water tower. This is our water storage, our snowpack. That snowpack provides most of the stream flow, and that snowpack provides the stream flow, which then ends up in our reservoirs. Is this mic okay? Okay. I feel like it's, there's some other noise happening with it, but okay. If you guys are okay, then I'm okay. All right, so our snowpack provides our stream flow, which ends up in our storage reservoirs, and that's the water that we use to irrigate crops, that's the water that we drink, and that's the water that we water our, uh-oh. All right, how's that? Okay, so our mountain snowpack, that's our water tower, our water storage in the state of Colorado. And so here's our annual precipitation in the state of Colorado. Here's the Continental Divide. And we can see that the green, that's a greater amount of precipitation, and most of that is west of the Continental Divide. So when we talk about water in the state of Colorado, we have to talk about the Colorado River. All of the water, all of the snow, all of the rain that falls west of that red line ends up in the Colorado River Basin. And just to give you a sense of how much water this is, on average across the state, we get an average of 16 inches per year of precipitation. Grand Junction, where I just moved from, got an average of 9 inches per year. And the Front Range cities, Boulder 21 inches, Denver and Fort Collins 16. And then here in Aspen, well, we're not in Aspen tonight, but tomorrow night I'll be in Aspen. At an elevation over 8,000 feet, the average annual precip is 25 inches, and average annual snowfall is 176 inches. And we'll look in a minute at the relationship between the snow depth and the actual amount of water that's in it. So from a water supply perspective, we're not so much worried about this total depth of snow. We're more worried about how much water is actually in that snow. So in the Colorado River Basin, most of the basin gets less than 20 inches of rain a year. And a third of the basin receives less than 10 inches of precipitation a year. So most of the water in the Colorado River Basin is coming from only 15% of the watershed. And most of that area is in the high mountains in the state of Colorado, a little bit in Wyoming, a little bit in Utah, a little bit in Arizona. But we are truly the water producer for the Colorado River Basin. So our snowpack, excuse me, our snowpack is a really important piece of the water in the Colorado River Basin. And we're starting to see around the world as we study snowpack and water supplies and temperature changes and global climate change that global warming is having an impact on our snowpack. This was a study that was looking at data from the 1950s through 1997. And these are each dot, each circle is a snow course location. And if the circle is red, it indicates there was a negative trend from 1950 to 1997. If it's blue, there was a positive trend. And the size of the circle is how positive or negative that trend is. These are modeling data, but you can see that there is, across the western US, a reduction of winter snow accumulation. Globally, we've seen a decline in snow cover. We also see reduction in total amount of water that melts from the snow. Sometimes we have an intensification of that snow melt rate depending on the timing of the melt, how quickly it melts. And then there's a lot of uncertainty about how our snow melt will change as we may start to get more rain on snow events. So this would be spring rainstorms when you still have your snowpack, which can produce pretty remarkable floods and also may have effects on soil moisture as well. So there are a lot of interesting impacts related to temperature. Sorry. Sarah, did you open the same presentation that I had before? Okay, well, I guess we're going to do our primer on snow now. So I think it's, yeah. All right. So let's talk about what is snow. So snow is actually a three-phase system. So we have solid ice, liquid water, and air in snow. And the combination of those three will determine how light and fluffy the snow is, how great it is for skiing, how heavy it is for shoveling, how good it is for making snowmen or for having snowball fights, right? That wonderful, amazing solid ice portion of it are little ice crystals, and the ice forms a six-sided hexagonal crystal. And as those crystals develop in clouds, as those ice crystals get bounced around in clouds, they build and they grow, and the way they grow depends on the temperature and the humidity in the cloud as they grow. And, you know, we love seeing these beautiful symmetric snowflakes. This is actually created in a lab. It's a designer snowflake. And there's a great website. You can go look at all these designer snowflakes. They build them in a chamber where they regulate the temperature and the humidity of the snow so that the flake actually will build in a certain pattern. So we can see if temperature is colder, we get different shapes of snow, and if temperature is warmer or if humidity is higher. So the growth of those little ice crystals depends on what happened in the atmosphere as that snowflake grew. And to think about density of snow and snow water equivalent, we have to think about what's going on with how much liquid water we have, which has a density of 1, versus how much solid ice we have, which has a density of 0.9. So fresh fallen snow will only have a density of 0.07, so really light, fluffy snow, whereas once it settles and it's been sitting for a while, and we'll talk about what happens in that process as it settles, we end up with really dense snow, which can have a density of 0.4. So compared to water, so a density of about 40% of liquid water. So when we think about snow from the water perspective, like I said before, what we're really interested in is how much water is in the snow. And what we do, we measure that as the snow water equivalent, which we will call SWE, so SWE. So snow, how much water is in the snow? So let's look at an example. We have, let's say, 10 inches of snow depth. And if we were to melt that 10 inches of snow, we might get 2 inches of liquid water. So our snow water equivalent is that 10 inches times the 20% water content, which gives us our 2 units of snow. So we can talk about SWE, the actual inches of water in the snowpack, or we often also talk about snow from the perspective of the ratio of the depth of the snow to the depth of the liquid. And this is what you might hear, it's kind of a common thought that in Colorado, 12 inches, a foot of snow gives you an inch of water. Some of you may have heard that before. And so that's what we're talking about there, is that liquid to water ratio, a 12 to 1, 12 inches of snow to 1 inch of water. So just to give you an idea, if you have ordinary new snow right after falling, it may have a 20 to 1 snow to liquid ratio. Settled snow may have 10 to 1. When snow gets windblown, those crystals get damaged, they get banged around, and so your snow gets a lot more dense. And our snow to liquid ratio may be only 3 to 1, and then ripe snow, which is when it's melting, it's right at the melting point, may have a ratio of 2 to 1. So, and across the US, the average ratio, snow to liquid ratio, is 13 to 1. And so we can compare that heavy, dense snow that's really good for making snowmen, really good for snowball fights, the kind that you really hate shoveling. That's over here. That's our dense snow, where then this is a pretty extreme 2 to 1, 10 inches of snow depth producing 5 inches of water. That's a really high snow water equivalent. Versus, you know, the light, fluffy champagne powder that we love to ski, 20 inches of snow depth producing 1 inch of water. So the SWE, the snow water equivalent, is the depth of the liquid water. The SLR, snow to liquid ratio, is the ratio of the snow depth to the water. So from a water perspective, we want more of this over here. From a ski perspective, we want more of this. All right, so how does it vary across the US? Just to give us an idea of where we stand in the US, this is the lighter, less dense snow. The blue and green is the heavier, more dense snow. And not surprisingly, that heavier, more dense snow occurs in areas where the storms are going to come in laden with moisture and be able to dump heavy snow with a lot of moisture. As the storms move across the Sierra Nevadas, the Great Basin, and then finally hit us in the Rockies. And these polygons, the shapes here are not states, obviously. It's the National Weather Service Forecast Office regions. So the Grand Junction Forecast Office is our forecast office for Western Colorado. And the average snow to liquid ratio for the Western Colorado, Eastern Utah area is 15. So that's our great skiing that we have here in Colorado. All right, so the snow falls. We have ice crystals, we have liquid water, we have air in our snowpack. And as that snowpack sits, it starts to settle. And as it settles, the ice crystals break down, and the density of the snow starts to increase. So we have our fresh snowpack and then our settled snowpack, and that snow to liquid ratio changes as the snowpack ages, right? So we have the same amount of water, but our snowpack is settling. And so we can see over time, so this example here is on Berthoud Pass in Colorado, the density of the snow starts to increase as that snowpack settles, and we end up with more heavier, more dense snow. So what does that mean out in the field, in the mountains, and how does that translate into water that we can use? So here's our snowpack moving into our stream flows and into our reservoirs. And this process, what I'm going to focus on now is this process of our water transforming from its solid form in our snowpack into our liquid form in the rivers. And it's actually a really complex process. There are a lot of complicated interconnecting processes and other influencing factors that determine how that water gets transformed into how the snow gets transformed into the water that we see in our streams. So our snowpack tends to melt mainly from the top down. So here's our snowpack. The snow melt starts, the water starts to trickle through the pore spaces in the soil, in the snow, and then it hits the surface, and then it will infiltrate into the soil or run off over the surface. And we'll dig into these processes a little bit more in just a minute. But the key factors that are determining how the snow actually melts are solar radiation, so some of that shortwave solar radiation that hits the snowpack is reflected. Snow is very highly reflective. It has a really high albedo, high reflectivity. But if the snow ends up with any kind of dust on the surface that makes it a little bit darker in color, it will absorb a lot more of that solar radiation. And so depending on how clean your snow is or how dirty the snow is, solar radiation can play a really big role and can be the dominant factor in how the snow melts. The other thing, of course, is temperature, and then wind. So those are our three main factors that drive our snow melt process. And in the field, we may have, so here's a little schematic of our little hill slope with our snowpack. So there's our water in our snowpack. And remember that water will infiltrate into the soil. So another important reservoir of water on a hill slope in the Colorado Mountains is how much water is in the soil. And then another piece is how much is actually in the groundwater. So this is the water that has percolated down, and all of the pore spaces in this rock or in this sediment is completely full of water. And then, of course, we have our stream flow. So these are our main reservoirs of water in the mountains. And when we're trying to figure out and model and estimate how much water we're going to get in our reservoirs based on how much snow is in the mountains, what we have to think about is how does water move through all of these different reservoirs? How much vacancy is there in the soil? How much room is there that we need to fill up? How much is actually going to run off and make it to the streams, and how much is going to recharge our groundwater? So trying to figure out all the processes that move that water between those four reservoirs is kind of the key to our forecasting and modeling of what's our flow in the river going to look like based on our snowpack. So the main processes we have going on, one is sublimation, and this is the movement of water from its solid form to its vapor form. And we do lose a significant amount of our snowpack to the atmosphere. So this is snow going, it's like vaporizing, right, evaporating snow. The next process that's important is as soon as the snow starts to melt and that liquid water makes it to the soil surface, it will infiltrate into the subsurface. So that's the process that recharges that soil moisture. And this gets really complicated because it depends on how much clay is in the soil, how much organic matter, what's the root structure, and how much space is it? How dry were the soils when that snow fell the previous fall? So this infiltration piece is an important piece. And then some of that water will percolate down, recharge our groundwater, the water table, and that groundwater flow to our streams, that's what we call our base flow. That's the flow to the river that sustains through the year when it's not raining and we don't have runoff through over the surface. So that recharge of groundwater is a really important piece of sustaining the flows in our river. And then once we overwhelm infiltration capacity, then we can get surface runoff to our streams. And it's these near surface and surface processes that contribute greatly to our big peak snowmelt flows that we have in our streams each year in the late spring and early summer. There are a couple other factors that complicate this. Like I mentioned, this notion of dust on snow. There's been a lot of research, and especially down in southwest Colorado and also in the Grand Mesa, looking at what is the impact of having a dust layer on our snowpack. And as far as the timing of when the snow melts and how much water do we actually get to the river. The other piece, like I mentioned earlier, is rain on snow. And as climate changes and climate warms, we have more rain events in the spring than snowfall, or we can. And when it rains on the snowpack, what does that mean? How much water infiltrates? Does that affect how much gets to the groundwater versus how much makes it to the stream? So the point here is that there are a lot of complicated factors that interact, and there's also a lot of uncertainty in how does our snowpack actually transform to stream flow. So for example, let's look at, this is the Cache La Poudre River up outside of Fort Collins from 1995. 95 was a big snow year in central and northern Colorado. I remember that because it was the year my daughter was born, and Vail Pass was closed for like 5 days, and I lived in Summit County, and the hospital was in Vail, and it was very dramatic, but big snow year. And then here, so this is the accumulation of that snow water equivalent through the winter. And it peaked, it was actually a really late peak that year, so it peaked kind of late May, early June, and so temperatures have warmed up, and here's the water, the river flow in the Cache La Poudre River responding, and then the snowpack diminishing, and then the stream flow going down. So that's really the kind of the typical pattern that we see throughout the Colorado mountains. So, so what we're going to look at in a little bit are some of the data that we've collected from our monitoring efforts on the Grand Mesa and in the Uncompahgre. But before I get to my monitoring, I just want to present an example of how warming plays a role. Warming temperatures can play a role in our stream flow and our water supply in western Colorado. So I just grabbed, this is just last winter. So 2018, you might remember, was a pretty warm year. We had a warm winter, a lower than average snowpack in a lot of watersheds in Colorado. And just focusing here, Colorado, much warmer than average January temperatures. Western Colorado, above average February temperatures. The whole state of Colorado, above average temperatures. And this is a pattern that we're starting to see pretty regularly now, that we're having months and weeks of above average temperature. So what does this mean for our snowpack and for our runoff? So the example that I'm going to use is actually from the year before 2018. And what we're going to look at first is this is the snow water equivalent through the winter, the median, which means for 50% of the time it was higher and 50% of the time it was lower. This is the average for that 30-year normal, right, 1981 to 2010. And this is looking at snowtail sites that are considered to be representative of the upper Colorado River Basin. So the upper Colorado River Basin, the main stem of the Colorado River, flows into Lake Powell. The dividing line between the upper and lower basin is just below Glen Canyon Dam, which is the dam that creates Lake Powell. So this is a selection of 17 snowtail sites that are often used to look at what's going on in the upper Colorado River Basin. So this is the median. Just for reference, this was last winter. So and notice this is water year October to September. So 2018 was pretty low snowpack, below normal. 2017 started out low, but then got above average, but then ended up being sort of normal. So what happened? So that's one of the questions. And just for reference, and to point out also one of the other challenges we have in Colorado is we have a very variable system. We could have a flood in one year and a drought year the next, and that's normal. So, so here was 2018 in blue, 2012 in red. 2012 was one of our worst drought years on record. And then 2017 in green, and 2011 in that bright blue, that light blue. So 2011 was a flood year, 2012 was a drought year. 2017 was a above average, and 2018 was a drought year. So this is a not uncommon scenario that we have to deal with as in the state of Colorado. And to manage our water, we have to manage for that kind of extreme variability. So that's one of the challenges that we face in the West. Okay, so what happened in 2017? March of 2017 was the hottest March ever in 123 years of record in the state of Colorado. It was also the hottest in New Mexico. It was 8.8 degrees Fahrenheit warmer than normal. So what did that mean for our snowpack? Well, if we look at just the Colorado snowtail sites, I should mention snowtail is the network of snow measuring sites. They're administered by the U.S. Department of Agriculture's Natural Resource Conservation Service. They're all located mostly above 9,000 feet in elevation in Colorado, and they're measuring snow water equivalent, as well as other meteorological factors as well. But they're our main snow data source. So the peak that year was March 14th. The normal peak is April 10th. The other thing that happened, I know this is really busy, but hang on and I'll get through it. In March, they were predicting, the Colorado Basin River Forecast Center, they were predicting that our snowpack, our runoff to Lake Powell would be 145% of normal, which would have been 10.4 million acre feet. We moved through that hot month, and the forecast goes to 138, only 9.9 million acre feet. We get to April, we're at 9.3. We get to April 18th, we're at 8.8. By the time we got to June 15th, the runoff to Lake Powell was only 8.3 million acre feet. So the take-home message here is that temperature really does matter when it comes to how does our snowpack translate into our stream flow. Okay, so now on to our monitoring in Western Colorado. There's one of my students who enjoyed all the monitoring challenges with me for a couple of years from Colorado Mesa. So this project was initiated by Dr. Stephanie Kempf at CSU. And she's got a crew, a team of graduate students that I've been working with now for a few years. I also had a team of students from Colorado Mesa University involved in this project, and now have a team of students from Fort Lewis College involved in this project. So I'm just one tiny little piece of this really big picture with a lot of people working together to make this happen. So the premise of this project is to try to understand how do we, what does our stream flow look like as it comes from these different zones, snow zones in the state of Colorado. So Stephanie had a graduate student who took satellite imagery from 2000 to 2017, and he did this globally, but we're just gonna look at Colorado. What he did is mapped what percentage of time do we have snow on the ground between January and June. And the areas that are shown in light blue, over this all of the satellite imagery for those 17 years had snow on the ground more than 75% of the time from January to June. So we call that our persistent snow zone. The area in yellow have snow on the ground between 50 and 75% of the time. The kind of pinky red color is our intermittent snow zone. So the snow's on the ground from 25 to 50% of the time. And all the gray is what we call low snow, which we're not looking at that. That's snow on the ground less than 25% of the time. So the question is, you know, if we monitor snow melt in these different zones, how does that transition from snow to stream flow vary in the different snow zones? So the rationale for this is that we know that that low elevation snowpack is more vulnerable as climate changes. And we know that it's sensitive to drought periods and warming temperatures. But our challenge is that each of these pink dots, those are our snowtail stations. Those are those NRCS snow measuring stations. And where are they? They're all in that persistent snow zone. They're all in the high altitude snowpack. So most of our snow monitoring occurs in that high elevation snow. But our stream flow monitoring is in lower elevations. And so we have an imbalance between where we measure snow and where we measure stream flow. And there's a lot of uncertainty about how much stream flow originates from that lower elevation snowpack. So the purpose of our study is to try to improve our understanding of the relationship between the snowpack and the resulting stream flow across Colorado. So we set up originally this network where these 6 sites are. Those were our original study sites, the ones in black, and then we've added a few more, which I'll talk about in just a sec. But they're designed to sample the different snow zones. And we analyze snow, soil moisture, temperature, air temp, relative humidity. And I just want to show you some of the challenges that we've had in just even deciding where to put the sites. So we wanted to monitor the Grand Mesa, a mesa, flat top mountain, pretty flat elevation on the top, steep topography on the sides. And so the transition from that persistent to transitional to intermittent snow zone as you dive off the side of the mesa happens really fast. So there's not a whole lot of room to get transitional stations in there. Then you add on top of that all the diversions, because we want natural watersheds. So there are a lot of little lakes and ponds and reservoirs and diversions on top of the Grand Mesa. And then you have private land, and then you have access issues in the winter, right? So what we ended up with are these 2 watersheds, and I've highlighted them here. Their elevation, here we go. Elevation, the top one is 9,900, and the second one's 9,600, which makes them really close together. When you're like, wow, is that really going to tell you what's the difference? But interestingly, the average precipitation is actually different. And as we'll see as we look at the data, we actually see differences between these sites, even though they're really close in elevation. Our intermittent site here, crazily, never flowed. And so it's kind of hard to look at the relationship between snowpack and stream flow if you have no stream flow. So we ended up eliminating that station. And then we added some new ones. So our final 6, so here are 2 on the Grand Mesa. We have 1 in the Colorado National Monument, and then we have 3 in the Uncompahgre Valley. So this upper one in the Uncompahgre, down here in purple, is up at the very top of Red Mountain Pass at 12,300 feet. And you can sort of see the gradation from 12,000 to 10,000 to 8,000 feet. And here on the mesa up at 9,000, and then the National Monument at about 7,000. And annual precip from 12 to 36 to 40. So we're measuring that gradation from low elevation snowpack to high elevation. And just to give you an idea of what do these sites look like, here's our top site on the Grand Mesa in winter and in summer, and our middle site on the Grand Mesa in different seasons, and then the National Monument site, just to give you a sense of sort of what they look like. What are we doing at these stations? Well, adventures in monitoring. So one of the first things you have to do then, once you decide where to put them, is that you have to install them. And so that means hiking, carrying lots of gear in. And yes, John Hammond hiked the whole way up with that pole in his mouth for a mile up a canyon. You're digging in snow, hanging off of bridges, getting really creative, attaching things to trees, digging in dirt and rain and standing in streams. And for the students, it's been a lot of fun and a great adventure also. So we're measuring rainfall, which that's great in the summer. Those tipping bucket rain gauges don't work very well in the winter, so that's another challenge. We measure snow depth, and we're on a pretty low budget with our little operation here. So we have a snow camera that points at snow stakes, and again, sometimes it's not so much fun when you I think Craig had just fallen into a snowbank there. We do transects and measure snow depth or soil moisture. We also do cores. So we take a PVC pipe and core the snow and put it in a bucket and weigh it. And a group of students having a good time out there. We measure stream flow, and it's just fascinating to watch these sites change throughout the year. One day at our Ouray site, over the course of just the day we were there, the stream flow came up 20 centimeters in the river while we were doing our monitoring. And they're in beautiful locations. This is a different kind of gauge, and I'll show you some interesting things about that. We're also measuring soil moisture and temperature. And then we have, well, not wildlife, but we have cows that knock things over, and birds that decide they're going to peck on our gauges. And at one site, this was a fox. He's actually got a rabbit in his mouth. There were other pictures. We had a cougar wander through, and then a bear come investigate. And then we have challenges. Sometimes you show up at the site, and this is what you find. So you spend a while digging. This is Craig digging out the rain gauge. You can barely see him. And there's actually equipment under this little pile here. These are the stream flow gauges completely buried in snow. This time we couldn't even find it. We never found the gauge that day. I had to come back later. And then that other stream gauge in Ouray, last winter we had no snow, and so everything froze solid. And I chipped away for a while, brought my students back with a propane torch, and then someone had the brilliant idea, let's heat up water in the snow shovel and pour it on the pipe so that we can free up the stream gauge. So you have to get creative. It's been a lot of fun. It's not always easy, but we're learning some things. So what did we learn from all of this monitoring, other than that duct tape is a good thing to have in your backpack, and that channeling MacGyver to think of boiling water in a snow shovel can be a good idea. We've also had some challenges with data management. We have 3 institutions. We have thousands of files. We have 20 gigabytes of data and multiple students working on it. And so it's been an interesting challenge. All right, 5 more minutes. Okay, so what we've learned, so our first year was water year 2016. This is our first year monitoring on the Grand Mesa. These 2 sets of satellite images, these are the Front Range sites. And on the right are the Grand Mesa sites. So this is April, May, and June. And in that first year of monitoring, one of the things we found was that the Front Range sites generally had deeper snowpack, and that snowpack lasted longer than the Grand Mesa sites. So that snow on the Front Range sites persisted in more areas into June, whereas on the Grand Mesa, almost all of it had melted out in early June. this year, that was our first year monitoring the Grand Mesa. We had so many instrument failures that we had some real challenges, and I'll share some of those with you too. It really has made me appreciate the kind of monitoring that happens in like the Arctic and the Antarctic, you know, where like we're going maybe a month between visiting these stations, where you have to set up a station in extreme cold and really extreme conditions and leave it there for months on end, and hopefully your equipment is still working all that time. So it's been interesting. So in water year 2017, this is just to help you see, this is the top of the Grand Mesa, this green area. This is the Mesa Lake Snowtail Site and the Park Reservoir Snowtail Site. So those are the snow monitoring done by the Natural Resources Conservation Service, the NRCS. These are our two little sites, our persistent and transitional site. And we were pretty excited to see that we're tracking pretty well with the snowtail sites at our persistent gauge. So the peak snow water equivalent happened about the same time at our site as the Park Reservoir site. But we saw the peak snow water equivalent at our transitional site was in January. And so there really was a big difference, even with that small elevation difference, but there is a temperature difference between those two sites. So it helps us see that how sensitive that snowpack is to small temperature differences. So the upper site had a SWE of 0.8 meters, so 800 millimeters, and the transitional site had a peak SWE of only 600. And the transitional site melted out earlier. So again, that temperature is important. Okay, this is the last bit of data. I have 3 slides, more graphs, and we'll step through them. So this is our final like kind of wrap up of all of the data that we've collected. For each site, we have precipitation, we have soil moisture, we have snow depth, and stream flow, and then air temp and soil temp. Okay, so let's pick through each of the sites, and there's just a couple of interesting things that I wanted to point out, and then we'll wrap up. So starting in the Uncompahgre, so this is top of Red Mountain Pass, Senator Beck Basin. It's a basin that's monitored, been monitored for several years now by the Center for Snow and Avalanche Studies in Silverton. So we're working with them. They've let us put a little bit of equipment in there, and then we're also using some of their data as well. We only have 1 year of data there so far. But I just wanted to point out, this is that classic pattern of here we have accumulation of snow, and then as that snow melts, our stream flow starts to peak, the snowpack diminishes, and then the stream flow goes down. We can see through the winter, soil moisture is low, and as the snow starts to melt, our soil moisture increases, and then it reaches a peak, and then it starts to decline through the summer. If we move down in elevation to Ouray, now here we can see we have less snowpack, and there's not a gap in snow there. That was because the camera didn't work. So this is those equipment malfunctions that are just, it's crazy. We have 1 month, the last picture, which was taken 15 minutes after we left, is of a very hairy black armpit, like a bear, climbing down the tree. And the power cord was pulled out of the cable. So 15 minutes after we were there, a bear climbed down from the tree and pulled the power cord out of the camera. All right, so yeah, we don't have a lot to show. And then this was that stream with the crazy ice that we were chipping at. That stream gauge kept getting completely buried in sediment. And we ended up having to pull it out, and we actually aren't even using this site anymore because this stream is just so mobile with so much material, it buried our sensor. And then we get down to that intermittent site. It's near Ridgeway, and what we see is minimal sporadic snowpack, a little pulse of stream flow, and no stream flow at all for the rest of the year. If we go to the Grand Mesa, we have more data. This is our top site at the Grand Mesa, so here's our first year, and then 2017, which was a bigger year, and then 2018, our kind of drought year. Now, what I want to point out here is notice this water peak, the black line, is really, it's not very peaky, right? It makes a little peak, but then it sort of has this really long tail, and then in 2018, we didn't have much of a peak. The Grand Mesa is really interesting geologically, and the groundwater there is really important. So what we're finding is that on the Grand Mesa, there's a lot more water moving into that groundwater then producing this big snowmelt peak. So again, contributing to that complexity of that connection between snowpack and stream flow. The transitional site, our stream gauge, the data are a disaster. That's another whole nother story. The stream gauge keeps sinking in the mud. So that's been a problem. And here's our new intermittent site. And again, no stream flow. So we're having a little bit of problem with our west slope intermittent sites with no stream flow. So finally, comparing our top sites, Front Range to West Slope. This is the Front Range Michigan Creek site. And here's water year 2016, 2017, 2018. They did not experience the kind of drought year that we had on the West Slope in 2018. So here's our Grand Valley site. Lower snowpack in 2016, pretty comparable in 17, and then in 2018 we had much lower snow. So notice this discharge, the big peaks, and then see how different it is on the Grand Mesa. So that underlying what's going on with the geology underneath can play a really big role in what happens with our stream flow. And then here's our Uncompahgre, Senator Beck, Red Mountain Pass site, but the scale is different here, so this is actually not as high. All right, so let's look at this year. This is my last slide, last bit of data. Where are we now in 2019 compared with some of these other years? So back to our Lake Powell 17 group, so kind of our representative, what's going on for Lake Powell. Here's 2018, our kind of droughtish year last year, 2017, and then the red line there is 2019. So I pulled this data on Monday, and at that point, the upper Colorado River Basin, these representative stations were at 117% of normal. And normal is average of 1981 to 2010. And, you know, if we look throughout the West, the color here, green and blue, is above average. Or green is about average, blue is above average. So in the West, we are doing really well as far as our total snowpack in the West. And our upper Colorado River Basin is mostly above average. And what's the prognostication for the future? Of course, we can't forecast out very well, much past about 7 days. But one of the things we do know is we are in an official declared El Nino. And when we look at what does an El Nino mean, in general, it means that the southern part of the U.S. tends to be wetter than normal. And so the latest prediction from NOAA's Climate Prediction Center is showing above average precipitation for the southern U.S. So that's where we are now for our snowpack, and we'll see what happens for our stream flow as that all starts to melt, recharge our soil moisture, and become runoff. So our take-home message is Colorado snowpack, that is our water supply. Temperature does matter, but there's still a lot of uncertainty in how does that snowpack translate into stream flow, and monitoring can be challenging, but it's also very valuable as we're learning more about our snowpack and our water. That's it. Thank you very much.
So awesome, Gigi. We have a microphone here for questions, and we'll see what happens. Thank you.
Does it really make sense to keep changing normal every 10 years to the previous 30 years? Shouldn't it be 50 or 70 or however many years we have data for?
That's a great question. And I think my take-home point there is to always check to see what is the normal that is being compared to. Because you might find sometimes, depending on when a study was done, it may be comparing to the 1970 to 2000, or it may use the whole period of record. I mean, sometimes we do 1895 all the way to the present, whenever the record started. Does it make sense? I don't know. It's a standard. And so I don't have a good answer to that. I'm sorry.
In today's Aspen Daily News, there was an article, and there will be a discussion tomorrow night in Basalt about cloud seeding, pros and cons. I'd like to know your opinion on that.
I was prepared. I read that article today, and I'm glad I did. Dave Kanzer, who will be answering questions tomorrow from the Colorado River District, he's a great source to get more information about cloud seeding. But there is research that's shown that cloud seeding can have a positive effect on the amount of precipitation that you get, up to maybe about 5% or so. There's also a lot of uncertainty about how well it works. There is a lot of cloud seeding happening in western Colorado. It's very well organized, and they have a meteorologist who predicts when they should actually cloud seed. It is controversial. I recommend that you go tomorrow night. I wish I could go too, but I'll be in Aspen giving this talk again. So I think that's a great opportunity to learn more about what's going on with cloud seeding, because it's a fascinating concept that's been done for a long time. And again, like I said, there's still a lot of uncertainty about how effective it is.
So there's trans-mountain diversion, sends water from the west to the east. And I'm curious if we'll ever have water sent from the east to the west.
That's an interesting question. So we tend to move water around to where we need it. We, in the state of Colorado, 80% of our water precipitation falls west of the Continental Divide, but 80 to 90% of the population is east of the Continental Divide, and so we move the water to where the people are from that perspective. So do you mean from eastern Colorado or from like the Mississippi River Basin?
Just from the Rocky Mountains. You know, there's apparently a lot of snow in the middle mountains, and Denver is just building population, and we're going to require a lot more agriculture to deal with the populations, and there's a lot of agriculture to be had in the west.
Yeah, that's a great point. And in the state of Colorado, more than 80 of the water that we use, more than 80% of that goes to agriculture. So agriculture is our biggest user of water in the state of Colorado and in the western U.S. And it's important. We all need to eat. So that is an important piece. Our entire water system in the United States is not the most efficient system. And so as we sort of bump up against limits in the supply of water and our growth of population and need to grow more food, there is potential for us to improve efficiency as well. So that's another possibility for dealing with our growing population.
All right. No more. Thanks so much, Gigi.
Right,
and she'll stick
you.
around and have more side conversations if you'd like. And we'll see you next week. Same place, same time.